Salam, peace be upon you. My name is Muhammad Laiq Siddiqui, the father of Holophase. Part 34, Book 9, Synthesis of Physics, Rewriting all of physics in one grammar. Generating classical mechanics, trajectories and forces as phi sentences. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We stand at the highest lookout point of our long climb up the master tree has been akin to learning to read a cosmic musical score. First, the individual notes, then chords, then harmonic rules, then entire symphonic forms. We have learned how phi, through its derivatives, generates waves, defects, and dynamics. We have sworn oaths of honesty, defining how the grammar could fail and where its current maps grow faint. Now, we reach the summit and turn to face the breathtaking vista below. We see the entire landscape of human knowledge, the valleys of classical physics, the towering peaks of relativity, the shimmering probabilistic forests of quantum theory. And we ask the ultimate question: can the single language of phi speak all these dialects? Can one grammar, starting from one field, truly generate the stories of balls flying, light bending, electrons interfering, and space curving? Today, we begin the final, glorious book. Book 9.9, Synthesis of Physics. And we start with the physics most familiar, most intuitive, the physics of our everyday world. In Part 34, Generating Classical Mechanics, Trajectories and Forces as Phi Sentences, we will witness a miracle of translation. We will watch as the ancient, powerful language of Newton, with its masses, forces, and parabolic arcs, emerges not as a fundamental truth, but as a compelling dialect spoken by phi when certain conditions are met. Our anchor image is a master linguist listening to a complex, ancient poem being recited in a modern dialect. He doesn't hear two different poems. He hears the same core narrative, the same emotional arc, expressed with different accents and local idioms. He can translate one into the other, revealing the deeper, universal story beneath. Today, we are that linguist. Phi is the universal tongue, and Newton's laws are the local dialect. We will learn the translation rules. Here is the beautiful puzzle of this part. Classical mechanics is about discrete particles, with definite positions and velocities, responding to forces. But our holophase grammar knows only one continuous, undulating field, phi. There are no little balls, no invisible strings of force in its fundamental vocabulary. So how can a field of pure change produce the crisp, predictable arc of a thrown baseball, or the elliptical orbit of a planet? How do lumps and particles emerge from a smooth tapestry? And if they do, will they obey Newton's rules? The answer is a story of emergence and approximation. It is the story of how certain special, persistent patterns in the phi tapestry, localized, coherent bundles of change, behave as if they were independent objects, and how the ambient shape of the tapestry itself gently guides these bundles along paths we call forces. Let's begin by constructing a particle from pure phi. Imagine a vast, calm meadow of tall grass. This is our background phi field, gently undulating. Now, imagine creating a special pattern, a tight, circular region where the grass is twisted into a stable, rotating knot. From a distance, this knot looks like a distinct object sitting in the meadow. It has a location. It has a sense of internal swirl, a kind of spin. This is our first hint of a particle-like entity. In the mathematics of phi, such a localized, persistent excitation is called a soliton, or a lump. It is not a separate substance. It is a particular knot of phi's own activity, a coherent echo that holds itself together. The mass of this lump is not some extra stuff injected into it. It is a measure of the intensity and stability of that knot, how much oomph or resistance to change is packed into that localized pattern of phi's motion. A more intense, tighter knot has higher effective mass. It's harder to push around because untying or reshaping that specific phi pattern requires more effort. Now, how does this phi lump move? If the meadow is perfectly flat and uniform, a stable knot might just sit there. But suppose the meadow is on a hillside. The tapestry of phi itself has a gentle slope, a smooth gradient in its background value or in the way its echoes interact. Our knot, our particle, finds itself in this sloping landscape. What happens? There is no external hand pushing it. Instead, the very structure of the phi field in which the knot is embedded guides its evolution. The knot's own internal dynamics, coupled with a sloping background, cause its center, the peak of the lump, to drift downhill. This drift is what we perceive as force. The force is not an actor. It is a description of the particle's response to the shape of the phi landscape. A steeper slope means a stronger drift, a stronger force. This is our first monumental translation. Newton's first law. An object in motion stays in motion unless acted upon by a force. In phi language, a stable phi lump in a perfectly flat, uniform phi background will maintain its state of internal motion, its momentum echo, indefinitely. Its center will drift at a constant rate. The force needed to change that motion is just the slope of the phi landscape. Now, the most famous equation. F equals ma. Force equals mass times acceleration. In our translation, F, force, is the steepness of the phi landscape gradient at the lump's location. Technically, it's the negative gradient of an effective potential energy function that emerges from phi's configuration. M, mass, is the lump's inherent resistance, the intensity of its knotted pattern. A, acceleration, is the second time derivative of the lump's center position, how quickly its drift rate changes. The phi grammar naturally produces a relationship where the lump's acceleration is proportional to the landscape slope and inversely proportional to its own stability intensity. It writes the sentence: slope of phi landscape, approximately lump intensity, times rate of change of lump's drift. This is F equals ma, translated into the dialect of fields and gradients. Let's explore the triunity of classical mechanics emerging from phi. The time echo of classical motion, the predictable trajectory. A planet orbiting a star is a phi lump, the planet moving in the deep, funnel-shaped phi landscape created by another, much larger phi lump, the star. The time echo is the clockwork ellipse. The position of the planet at any future time can be calculated with exquisite precision from its current position and drift rate, velocity. This predictable sequence is the hallmark of the classical limit emerging from the underlying, possibly more complicated, phi dynamics. The space echo of classical motion, the parabolic arc. Throw a baseball. It follows a smooth, curved path, a parabola. This shape is the spatial signature of a constant downhill slope, gravity, acting on a lump with initial sideways drift. The space echo is the graceful, deterministic curve. It is the visible trace left in space by a lump guided by a simple, smooth gradient in the phi tapestry. The motion echo of classical motion, conserved momentum. If you slide a puck on perfectly smooth ice, it keeps going. Its drift rate, its momentum, stays constant. Where does this conservation come from? From the phi grammar's symmetry. If the phi background is uniform in space, no slopes anywhere, then the rules of the game don't change from one location to another. This spatial symmetry, via the deep principle we met in Book 9.4, Noether's theorem, guarantees a conserved quantity, momentum. The motion echo is the persistence of drift. The phi lump's constant motion is a living memory of the uniformity of the space it moves through. Now, let's locate this grand synthesis on the master tree. This is the foundational node of Book 9.9, Synthesis of Physics. The classical mechanics synthesis node depends utterly on everything we have built, on the concept of persistent lumps from topological production in 9.2, on gradient-driven dynamics from the action principle in 9.4, and on the emergence of effective laws from hierarchical generation in 9.6. It enables the next, more subtle syntheses, electromagnetism, quantum theory, and gravity. If we cannot recover the familiar world of balls and orbits, the entire edifice crumbles before we even approach the mysterious. This node is the keystone in the bridge between the fundamental language of phi and the tangible world of human experience. To see this translation in action, let's light lanterns from different domains. A near lantern from crowd flow. Imagine a dense crowd in a city square. Each person is like a complex, conscious agent. But from a helicopter view, we see emergent lumps and flows. A dense knot of people, a crowd lump, forms near a street performer. The shape of the square, with buildings, fences, and open pathways, creates a landscape. Exits are low points, walls are high ridges. The crowd lump naturally drifts toward exits, flows around obstacles. You could write effective equations of motion for the crowd's density, with forces arising from the geometry of the space and the desire to move. The fundamental substance is individual people with their own free will, akin to fundamental phi dynamics. But the large-scale classical behavior is that of a fluid-like field obeying gradient forces. The crowd's motion is a phi sentence, a middle lantern from weather systems. A hurricane is a magnificent, coherent structure, a lump in the atmospheric field. It has a clear location, it spins, internal motion, and it moves across the ocean. What forces act on it? The pressure gradients in the larger atmospheric field, the Coriolis effect from Earth's rotation, a background curvature. Meteorologists plug these effective forces into equations of motion to predict the hurricane's path. The hurricane is not a separate object. It is a self-sustaining pattern in the continuous fluid of the air. Its classical trajectory is an emergent property. The hurricane is a phi sentence written in the dialect of fluid dynamics. A far lantern from planetary orbits in the 17th century. This is the historical moment of synthesis. Johannes Kepler, using Tycho Brahe's painstaking data, described the motion of planets, ellipses, equal areas and equal times. He described the space echo and the time echo, but he had no motion echo, no concept of force or inertia. Then came Newton. He synthesized Kepler's descriptions into a causal grammar, the inverse square law of gravitation, and his laws of motion. He provided the force that explained the curves. In our journey, Newton played the role of the synthesizer who discovered the effective dialect. We are now playing the role of meta-synthesizers, showing how Newton's dialect itself emerges from an even deeper grammar. We are standing on Newton's shoulders to see the deeper landscape of phi. What is the specific language role of classical mechanics within the holophase? It is a translation manual or a coarse graining filter. It is a set of rules that says, when you have a regime where phi patterns are 1. Localized. Lumps are sharp compared to their separation. 2. Persistent. Lumps don't easily radiate away or dissolve. 3. Moving slowly, compared to the speed of internal echoes, like light speed. Then you can safely translate the continuous phi story into the discrete object story of masses and forces using this specific dictionary. It is a production rule for generating a simplified, highly useful summary of complex phi narratives. The core question this part asks about phi is, under what conditions do stable, localized configurations of phi arise, and do their center of mass motions obey the same variational and conservation principles that we know as classical mechanics? We are moving from asking how phi changes to asking how it impersonates Newton. What does this synthesis do? It unifies our understanding, showing that the everyday world is not separate from the fundamental fabric, but a natural, coarse-grained expression of it. It validates the holophase grammar by requiring it to pass the most basic test, reproducing the physics we know best. It provides a template for how to perform syntheses with more complex physics. It demystifies classical concepts like mass and force, revealing them as derived, effective notions. Now, stability and change. This classical synthesis holds in the regime we defined, for slow-moving, persistent lumps. It breaks down spectacularly when those conditions fail. When lumps are not persistent, radioactive particles, or are not localized, electron clouds in atoms, or move at speeds comparable to the internal echo speed, relativistic particles, the classical dialect becomes a poor translation. We must then switch to quantum or relativistic dialects of phi, which we will explore in later parts. This breakdown is not a failure of phi. It is a boundary of the classical translation manual, just as we mapped in the last part. This brings us to the essential falsifiability thread. The claim is not vague, it is precise. The prediction spine. For any system successfully described by classical mechanics, a swinging pendulum, orbiting satellite, rolling car, there must exist. 1. A plausible phi model, a specific form for its Lagrangian or dynamics. 2. A stable, lump-like solution in that model. 3. A derivation showing the lump's center of mass motion obeys m times a equals minus the gradient of v, where v is an effective potential emerging from the phi model's background. The fail condition, falsification. If we take a quintessential, well-tested classical phenomenon, say the simple harmonic motion of a mass on a spring, and prove that no phi model of reasonable complexity can yield an effective potential v of x equals 1/2 kx squared, the spring potential, and produce a lump with constant effective mass m whose motion matches the observed oscillation period, then the claim classical mechanics is a phi sector fails for that phenomenon. If we cannot recover Hooke's law from any phi story, the synthesis is broken. Let's design a measurement scene that embodies this. A concrete, high-stakes measurement scene, the phi pendulum. We don't just look at a normal pendulum and say phi explains it. We build a system explicitly designed from a phi principle and see if it behaves classically. The system. A thin, flexible magnetic strip clamped at one end, hovering over a grid of precisely controlled electromagnets. We program the grid to create a specific, computable phi landscape. The strip's bending represents a local phi value, its curvature. The magnetic interactions are designed to emulate a simple phi model Lagrangian with a self-interaction term that encourages the formation of a stable kink or lump along the strip. The experiment. We excite the strip to create a single, clear kink. We then program the electromagnetic grid to create a gentle, parabolic well landscape, our effective potential, V. We release the kink and track its position over time with lasers. The classical prediction. The kink should oscillate back and forth in the well with a period t that depends only on the depth of the well, the strength of our programmed V, and the intrinsic mass of the kink, determined by the strip's stiffness and magnetic coupling. Its motion should be a near-perfect sine wave. The pass condition. Synthesis holds. The measured oscillation period matches the prediction derived solely from the parameters of our programmed phi model, the Lagrangian coefficients, and the resulting calculated effective mass and potential. The kink obeys F equals ma, where F and m are not input by hand, but emerge from the phi dynamics. The fail condition. Synthesis fails. The kink's motion is erratic, dampens out too quickly in a way not accounted for by simple friction, or oscillates with a period that cannot be linked to the emergent parameters of the phi model. This would show that for this clean, engineered phi system, the classical translation manual does not work. The link between lump dynamics and Newton's laws would be broken for this instance. This is the rigor required for true synthesis. It's not a poetic metaphor. It's an engineering blueprint that must yield testable numbers. Let's cultivate a practical recognition skill. You can train your mind to see effective classical behavior emerging from complex underlying grammars everywhere. Look for the lump in landscape. Watch a bubble rising in a glass of soda. The bubble is a coherent lump of gas. The landscape is the liquid pressure gradient, high pressure at the bottom, lower at the top. The bubble drifts uphill against gravity, buoyant force, at a roughly constant speed, terminal velocity. You are seeing an effective force, buoyancy, emerge from the interaction between the lump and the gradient of the surrounding field, pressure. Observe traffic congestion forming on a highway. A jam is a lump of high-density, slow-moving cars. An on-ramp introduces a disturbance, a slope in the traffic flow field. The jam may propagate backwards as a standing wave, a kind of motion of the lump. Traffic engineers use fluid dynamics equations, classical field equations, to model this. Consider your own decision to walk toward the kitchen when hungry. Your body is a fantastically complex lump of biological processes. The landscape is a gradient of perceived comfort, discomfort, hunger here, food there. Your motion toward the fridge is an effective, coarse-grained description of trillions of cellular actions. You are a phi lump moving on a motivational landscape. Whenever you see a distinct thing moving predictably in response to some gradient of height, concentration, desire, pressure, you are witnessing the classical dialect in action. You are seeing a candidate phi sentence. We must connect this first synthesis directly to the heart of the holophase vision. We have added no new ingredients, no mess stuff, no force particles. We have only used the grammar we already built. A field phi, its ability to form stable knots, solitons, and the principle that dynamics minimize a narrative cost, the action. From this alone, the concepts of object, inertia, force, and conserved momentum crystallize out. They are not axioms, they are theorems in the phi language. The ball on the landscape analogy is not just an analogy. It is, in a mathematically precise sense, what is literally happening at a more fundamental level. The ball is a lump in phi. The landscape is the ambient shape of phi. That of this synthesis is therefore a derivation rule. It is a meta rule that takes a high-level sentence in the classical physics book, the planet orbits the sun in an ellipse, and shows how to derive it step by step from a chapter written in the fundamental phi grammar book. What does this synthesis do for our understanding of phi? It grounds it. It proves that phi is not an abstract philosophical idea disconnected from the world of stones and stars. It is the very substance of those stones and stars, speaking in a dialect we have understood for centuries. Now, let's sound the triunity refrains one more time, now fully aware of their classical manifestation. The time echo of synthesis, historical unification. Just as Newton unified terrestrial and celestial mechanics, showing the same rules govern the apple and the moon, we are now unifying Newtonian mechanics and fundamental field theory. The time echo is the collapsing of separate histories into one lineage. The story of the flying ball and the story of the undulating phi field are revealed to be one story told at different volumes. The space echo of synthesis, the unified landscape. The space echo is the realization that the space of classical positions and the space of phi field configurations are not separate arenas. They are different views of the same terrain. The planet's position in space is the address of a phi lump's peak. The gravitational potential landscape is a slice through the multidimensional phi tapestry. The motion echo of synthesis, the conserved current. The motion echo is the unbroken thread of conservation. The momentum that stays constant in the sliding puck is the same conserved current that fell out of spatial translation symmetry in the phi action. It is the same flow viewed through different lenses. The synthesis shows the flow is real. The lenses are choices. This is where we stand on the master tree. The classical mechanics synthesis is the first and most critical fruit on the highest branch of Book 9.9. Its roots drink from the entire tree. Its success allows the next fruits, electromagnetism, quantum theory, gravity, to grow with confidence. If this fruit were rotten, the rest would be inedible. If you want to see the full mathematical derivations and exact equations behind this idea, the rigorous derivation of effective particle motion from solitary wave solutions, the precise mapping between phi model parameters and mass, force, potential, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. We have completed our first major translation. We have seen the world of Isaac Newton rise, fully formed, from the single field of phi. It is a moment of profound beauty and simplicity. The arc of a projectile, the swing of a pendulum, the orbit of a moon. These are not impositions on reality. They are natural, inevitable sentences that a self-reading, self-writing field like phi would tell about itself under certain conditions. Our journey in Book 9.9 has only just begun. Having secured the familiar ground of classical physics, we can now venture into more exotic territory. The next dialect we must translate is both elegant and pervasive, the language of electric and magnetic fields, of light and charge. In the next part, we will see how phi writes the stories of electromagnetism. Before we end, the mandatory zoom out to hold our scope. Classical mechanics as a phi dialect shows us that particles and forces are not primitive. They are grammatical constructs, persistent nouns and causal verbs, in a story whose only fundamental character is the verb-like field phi and its infinite modifiers. One field, phi, plus its infinite derivatives, plus the recognition that certain derivative patterns are stable and behave as if they were independent objects, obeying simple rules. From this, the entire predictable mechanical world emerges. We have not reduced the wonder of a flying arrow, we have deepened it. The arrow's flight is not just a path through empty space. It is a melody played by the cosmos on the single string of phi. As we conclude, hold the image of the master linguist. He has just finished translating the first epic poem, the Iliad of Newtonian physics, from the local dialect into the universal tongue. He smiles, because the meaning is preserved. The heroes are still heroic, the battles still grand. But now he understands the deeper roots of every metaphor. He is ready to translate the Odyssey of Maxwell, the haikus of Schrödinger, and the cosmic saga of Einstein. The Holophase grammar is that universal tongue. And we, having learned its alphabet and grammar, are now becoming its poets. Salam, and peace be upon you.